Welcome to module number 37. We're going to be discussing kernel methods. In 36, we discussed augmented methods. And kernel methods, I would say that in a nutshell, element by element in the data, you're looking locally around that element using perhaps a nonlinear fit. So recall the nearest neighbors approach, where what we're sketching here, the horizontal axis, you can think of that as our input, and the vertical axis are the output, or the horizontal axis is the explanatory variable, the vertical axis is the truth. And we have all of these points, and the blue might be the true function, and the green jagged function might be a nearest neighbors approach, where identifying the nearest neighbors around x0, this point might give us this yellow region. These are the nearest levels in terms of the input. And then we find a nearest neighbor level, this line, and that's where the green is. And as we move along horizontally to the right and to the left, each time that the yellow region, each time that we move it to the right and to the left, it could be that one or more points leave or enter the yellow region, and based on their vertical values, the green function moves. So overall, we have an average over the yi's that are among the k nearest neighbors of x, and k of x are the set of k nearest neighbors. And in the yellow rectangle, you can think of the height as representing the weights. Each of the different points has a different weight. But what if you said that the nearest points get a slightly higher weight, a bit larger than 1 over k, and the other points that are not quite as near get a somewhat lower weight? That might make sense, right? So let's move on. So here we're going to give a different weight to each of the elements of nk of x, and we're going to assign greater confidence to the nearer points, and we're going to taper away from the distant points. So f hat of x0 is going to be a summation over yn of a function that depends on x0 and xn, where that function may be larger when we're closer to x0 and smaller when we're further than x0. And you'll note that in the denominator, we're dividing by the sum of the k lambda functions. So one possible type of form for the k lambda function is a distance measure of the distance between x and x0 in the numerator divided by a width parameter lambda, meaning that if lambda is large, we're considering a wider range, presumably, and if lambda is small, we're presumably focusing on a narrower range. And actually, this width can be chosen automatically based on the profile of the points, right? Now, one thing that I'd like you to appreciate, let's go back to the previous page. So here in the classical nearest neighbors, when a point left or entered nk of x, that meant that, recall that we're averaging over the yi's, and the yi that leaves and the yi prime that enters, they're probably different. And because of that, there's a discontinuity in the green function. Whereas on the next page, hopefully we can create a kernel such that the points that are leaving or entering, they leave or enter with weight 0. And because of that, the green function, if we design the kernel appropriately, it'll be continuous. And just to make it clear, the kernel function is this k lambda function. Now, nearest neighbors can be used with kernels for regression. In the past, we discussed using nearest neighbors for classification, and we took a majority vote when we had binary labels. And if we had more than 2 labels in a classification problem, let's say 7 labels, we would take a plurality vote. Among the 7, the class that had the most members. And this can also be used for regression. We first choose the k nearest neighbors, and we perform a locally linear fit only among those k nearest neighbors. And similar to before, we can apply kernels by giving greater weight to the points that are closest to us and somewhat reduced weight to the points that are within the k nearest, but not quite that near. So that's it for module number 37.